Have you ever stopped to think about how your banking app, or even just your social media feed, can handle literally thousands of people all clicking and typing at the same time without just imploding? Well, today, we're pulling back the curtain on that hidden world. It's this incredible ballet of data management that's happening every single time you tap your screen.
Yeah, this is the big one. This is the central question that every single multi-user application has to figure out. So, how does it all work without completely breaking down?
So this whole challenge has a name. It's called concurrency. And let me tell you, it is a huge deal. If you don't have a really strict set of rules for who gets to do what and when, it's just a total free-for-all that would lead to some seriously, and I mean seriously, corrupted data.
When you have unmanaged concurrency, you end up with four main villains that can pop up and absolutely wreck your data's integrity. So yeah, let's actually dive in and meet these troublemakers. We're going to build a little mental map of the problems here.
And here they are. These are our main offenders. Now, while all four of these are pretty dangerous, for this explainer, we're going to zero in on the two most common, the two classic culprits, the lost update and the dirty read.
First up, the lost update problem. The easiest way to think about this, imagine you and a friend are trying to edit the same Google Doc, but you don't have that real-time syncing. The last person to hit the save button wins, and all the work the other person did, it's just gone, vanished. That is a lost update.
Okay, let's actually watch this play out step by step. You've got two transactions, T1 and T2. Both of them start by reading the exact same value, 10. Now T1 decides, I'm going to add 5, but before it can save, T2, which is still working with that original value of 10, subtracts 2 and writes its result back. T1 times finally saves its calculation, and poof, its update is totally overwritten. It's lost. The final value is wrong, and the data is corrupted.
All right, our second villain is the dirty read. And this one's even more sneaky. It's kind of like making a huge life decision, like quitting your job, based on a rumor you heard, only to find out a minute later that the rumor was completely false.
So here's the crucial point, right? If one transaction updates a value, and your transaction comes along and reads it before that first change is finalized, you are acting on totally unconfirmed information. If that first transaction fails, or if the user cancels it and it gets rolled back, well, your transaction has based its entire logic on phantom data that never really existed.
So how in the world do databases stop this kind of madness? Well, the most common solution is actually a really elegant and powerful system of locks.
Think of it like a library book. Lots of people can put a shared lock on that book. They can all read it at the same time inside the library. But only one person can get an exclusive lock, which is like checking the book out. Only they can take it home and write in the margins.
And what's really cool about this is just how simple the rules are. This matrix shows the whole logic. Two shared locks at once? Yeah, no problem. Everybody can read. But the second any transaction wants an exclusive or write lock, everything stops. It has to wait until absolutely no one else is holding any kind of lock on that data. Now, to keep all of this locking and unlocking organized, databases use the super strict protocol. It's called two-phase locking, or 2PL for short. You can think of it as the master plan that makes sure everything happens in exactly the right order. And the rule is simple, but it is incredibly powerful. First, you have the growing phase. This is where a transaction goes around and acquires all the locks it's ever going to need to do its job. Once it has everything, it does its work, and only then can it enter the shrinking phase and start letting go of those locks. The key is you can't go back and get more locks once you've started letting them go. But of course, this really powerful and elegant solution, it's not perfect. It introduces a brand new, very tricky complication, a scenario that computer scientists call a deadlock. A deadlock is the ultimate standoff. Seriously, just picture two people who meet in a narrow hallway. Each one is waiting for the other person to step aside, but neither of them will budge. They're just stuck. In the database world, it means transaction A has a lock on something that B needs, and at the same time, B has a lock on something A needs. Neither one can move forward. So how do you solve this? Well, the database has to play the tough boss. It has systems to detect this circular wait, and then it makes an executive decision. It literally picks one transaction to be the victim, cancels it completely, and rolls back all of its changes. This frees up the lock and allows the other transaction to finally finish its work.
Now, all of this locking and unlocking, it can slow things down. It impacts performance. And that's why databases don't just have a one-size-fits-all approach. Instead, they actually give developers control,
letting them choose exactly how strict these rules should be. And they do this using something called isolation levels.
This table here, this is the practical toolkit for developers. And it's all a balancing act, right? A trade-off between performance and perfect data consistency. If you're doing a banking transaction, you're going to want the highest, most paranoid level, serializable, no errors allowed. But if you're just updating a view counter on a blog post, maybe something way faster but a little less strict is totally fine.
And this is what it actually looks like in the real world. This isn't some abstract theory. It's a single, simple line of SQL code. With just this one command, a programmer can define the exact rules of engagement for their transaction, perfectly tuning the database's behavior to what they need. So all these rules create reliable transactions between different users. But what happens if the ultimate chaos strikes and the entire system crashes right in the middle of a transaction? I mean, how does the database guarantee your data will survive that? Well, for that, there's one final, absolutely crucial failsafe.
Say hello to the transaction log. This thing is the database's perfect memory. It's an indestructible black box. It's all based on a principle called write-ahead logging, which just means the database writes down everything it's about to do in this log before it actually does it.
And this is the ultimate guarantee. It means that even if you have a catastrophic failure, power outage, server explodes, whatever, the system can boot back up, read this log, and perfectly reconstruct the data to the last known good state. It can undo incomplete transactions, finish the ones that were committed, and make sure that your data is never, ever truly lost. This is the very foundation of database reliability.
So from thousands of competing users to a sudden system crash, databases are performing this constant, high-stakes balancing act between speed and safety. The next time you tap buy or hit post, just remember all the invisible logic making sure your data isn't just lost in the chaos. Which really leaves us with one question. In a world that demands ever-increasing speed, how much safety are we really willing to trade for it?